Hello, first thing I'd like to do is say thank you, Matt and Marie, for inviting me. It's a great pleasure to be an invited speaker at this workshop. Second thing, as we've heard, the title of my talk is Help or Hazard Towards Verifying Autonomous Robot Systems. So what I'm going to talk about is work carried out on a number of projects with several collaborators, and I'd like to mention those to start off with. I haven't mentioned them by name, and I will try and do that during the talk. But firstly, members of the University of Liverpool, who then moved to Manchester Autonomy and Verification Lab, and also work carried out on the Trustworthy Robot Assistance Project, the FAIR project, the RAIN project, and the Science of Sensor Systems software project. And the 4 of those are funded by the EPSRC and UKRI. So it's work done by collaborators, some by other people, some work I've been involved in myself. So what's the talk about? So autonomous robots, as we know, are being developed in all sorts of situations. For example, industrial transportation, we could have domestic, we could have healthcare settings. And what we'd like these things to do is be of benefit to society and to help people to improve things. We've got a few images down the side. So the top is robotics in a drone in an agricultural setting. We've got a pod further down. We've got the Ocado system right at the bottom, and we've got a collaborative manufacture setting as the second image. So what these robots will have to do is to act autonomously, and we'll need them to choose between a range of decisions. And those will have to occur in a whole load of different environments and different scenarios. So the environments they work in, they are going to change. They're not fixed. There might be aspects of them that are unknown. There might be hazardous environments. For example, the RAIN project dealt with autonomous robots in a nuclear situation, and the FAIR project about robotics in space. Additionally, like the second image we've got here, they may have to work closely or in collaboration with humans. And the key thing we want to make sure is that these robots are trustworthy, they're safe, they're reliable, and they do what they should be doing and not what they shouldn't be doing. So yeah, hazardous environments is what the team, the group have been working on for several years. So one of the projects, FairSpace, and that's the 2 left images here, was interested in things like rovers on the moon or on Mars, things like active debris removal, satellites operating in between around the Earth. The RAIN project was interested in using autonomous robots or robotics in nuclear environments to do clear up, to do a sorting of waste and things like that. The other project that I wasn't personally involved in, but some of the team was ORCA. So that's offshore assets and offshore robotics for the certification of assets. So things like, under the sea, oil rigs, wind farms, things like that. And the sort of common thing about all of these environments is they often have quite extreme conditions. There may be contamination. So in the RAIN project, we certainly had seminars from physicists telling us what radiation does to the joints on the robots. In space, there are communication delays that you've got to be concerned about. You've got to worry about where you're going to get the power from. All of these environments, like a lot of the ones on Earth as well, are unknown. There might be things we don't know about them. There are aspects we don't know in advance. And the crucial thing here is we want to make sure, as I said on the previous slide, that these robots, they do work properly, they don't break down. And if they do break down, we can recover from those breakdowns. It's difficult in these types of environments, particularly space, particularly nuclear, to get the robots out, to get an engineer to fix it if something goes wrong there. And in both these environments, in space and in nuclear, we don't want our robots to become part of the hazard. So we don't want our robot to become part of this space debris that someone's going to have to clear up after us. And we don't want it to, the robot just to become, a hazard and more nuclear waste. However, as part of the talk, as well as these environments, space and nuclear, I will talk a little bit about my favourite robot house environments as well. So we're talking about verification and validation. I'm sure I'm preaching to the converted here, but this is how I view verification and validation. So often verification is viewed as, are we building the system right? And validation is often viewed as, are we building the right system? So how this works is you've got a stakeholder that needs something, maybe they've got a satellite system, they've got a rover they want to send to Mars. Yeah, we need to specify what that robot should actually do. So that's specification. Robot then is designed. I mean, this might be more iterative than it looks on this diagram, and we build a system. So what verification is doing is checking the specification, the design satisfies the specification, the system satisfies the specification, and the system satisfies the design. So are we building the system right? What validation is doing is making sure that system was actually what the stakeholder needed in the first place, the person needed. So typical things you'll see me and other people talking about today and tomorrow for verification, things about formal verification. So that's what I tend to spend my time doing. Simulation-based testing or physical testing. So those are all examples of verification. And validation, things again like physical testing, you can see I've repeated this. A validation with users, saying, is this the system that you wanted, that you expected, and running through test scenarios. So why do we need verification and validation? Well, hopefully from the slide about hazardous environments, you'll have seen why. Well, firstly, we want to make sure the robot's doing what it's supposed to. And that's, in all situations. We don't want the robot to simply start doing other things that it isn't supposed to be doing. We want to make sure the robot's safe. So we don't want to harm people. We don't want to harm animals, buildings, other things. We want to make sure that the robot's reliable, that it doesn't break down all the time and people lose their trust in the robots. We want to make sure it's robust. So if something goes wrong, maybe a hole opens up in front of it, or its gripper fails, can the system cope with this going wrong? Can it use another gripper? Can it move around the hole? So we want to make sure it's robust and can do something if things go wrong. Can components be replaced for others? I suppose that's the gripper example again. Can we have new plans to achieve what we were trying to do? Key as well is related to, trust. Can we tell can we explain what we're doing? Rather than just a robot said so, system said so, can we say why those decisions have been made? And one of the robot collaborators I talked to, I think it was someone from the University of Lincoln, was talking about an experiment where I think a robot was in a public space, a shopping centre, shopping mall, something like that. And maybe it was in a university. And, there was a user there, and the user, or the people would come up and talk to the robot. And, the robot would supposed to be going to a particular place or helping the person get somewhere. And the first thing that the robot did was rotate. It moved around to try and work out where it was exactly at the time. And the users, the public, found this very confusing because they were trying to say, help me find a particular shop, or take me, in this direction, take me to the exit. And the robot then just turned around. So it would be helpful if the robot perhaps said, I'm turning around to check where I currently am. Security. So we don't want our robot systems to be hacked into. Driverless cars are there. We don't want to be able to hack into the driverless cars and people to use them for bad purposes. And to get all these systems on the market, we need to make sure regulators are involved and that these things can be certified. So we want to make sure we build systems that can be certified and the regulators are happy with the type of evidence we give to certify them. So my 3 types of verification I'm going to talk about first. So the first one, the thing where I work on most is formal verification. And as I'm sure most of you know, this is a mathematical analysis of behaviours using things like logics, and the tools that are often used are theorem provers or model checkers. So I often work with temporal verification and often using automatic tools and techniques that don't involve user interaction. So some theorem provers do involve user interaction. So there are other ways to do things, and not all verification is involving temporal aspects. So, you know, I love my operators that are always in the future and sometimes in the future. On the diagram at the bottom, I'm talking about model checking. So model checking, what a model checker does, it takes a model of the system. So here's an abstracted diagram of that. And it takes a property, you know, it's always the case the robot won't crash into the human, something like that. The model checker is an automatic algorithmic technique, and it checks the property we've got over all the runs of this system. What it outputs is either the property holds, right, great, we're fine, or it outputs a counter example, some run through the system where the property doesn't hold. And often when you're modeling these things, you know, if you get the property hold, well, that's good, but often the counter examples are more useful. So if you get the counter example, you might want to go back to the designers of the system and say, well, should this property actually hold anyway? You might want to check your model of the system. Often these models have to be abstractions of the real system. We want something that's discrete and finite usually. And so maybe you've taken too many abstractions in the first place, yeah, or maybe you have actually found a bug, in which case you report back to the designer, oh, I think I found a bug, and hopefully that can be fixed. So this is often an iterative process, and the model you take often has to be an abstraction of the system. I mentioned theorem provers as well up here. So we've also worked with temporal theorem provers. So instead of a model of the system, you have the representation of the system in logic here. And instead of a model checker, you'd have your theorem prover, and it would prove that the property is a logical consequence of the set of formulae describing the system. Output again, yes it is, or some form of counter example. Some of the theorem provers, the temporal theorem provers, sometimes are have less good interfaces for these for looking at the outputs here, but you know, that's you can do it. So where are we? I've said what the input is, I said what the output is. The other thing that I'm not going to talk about very much that could be classed as, or can be classed as, formal verification is runtime verification. So I haven't really been involved with runtime verification myself very much, but one of the members of the group, Angelo Ferrando and Rafael Cardoso, a lot of the examples I'm going to talk about in space, they've looked at runtime verification for that as well. So the verification techniques are model checkers and theorem provers that I've talked about before. You can think of as offline. We do them before the system is deployed. Runtime verification, you have your property that you would like to hold or you want to avoid, similar to before, but rather than having a model or a set of formulae, you're going to have a stream from a stream of behavior from the robot as it's running. You're going to check whether there's a monitor that checks whether the property does or doesn't hold, and then you raise a flag when it does or doesn't hold. So say this isn't something I have actually worked on. I'm sure Angelo and Raphael will say more in their talk later on. Simulation-based testing. So this is very useful, particularly in hazardous environments, because we might not be able to do tests in the actual environment. So here's a simulation that Raphael, that I mentioned before, did of the Mars Curiosity rover. Well, sorry, it's a simulation from NASA, but Raphael worked on this, putting an agent in there to control it. So we don't want to be sending a Mars Curiosity, a rover up to Mars and testing it out up there, because it's very expensive. If it doesn't work, we're in trouble, really. So doing simulations and testing those simulations are particularly useful in hazardous environments. Okay, the image at the bottom right down here is some work that Marie, our very own Marie, was working on with the University of Surrey, in particular Nikos Mavrakis and Yang Gao. And what this is a simulation of is it's a grasping algorithm trying to look at active debris removal. So there's a grasping hand here. It's trying to grasp some debris coming round, and this was a simulation done at the University of Surrey. Again, they don't want to be sending this thing up into space to try it out, so it's best to look at simulations first. The other advantages of doing simulation-based testing is you can do a lot more tests than you can in the real world. So maybe, you know, this is an example with our robot house. I think we've got examples of, you know, 10 tests or 100 tests done with people there. You know, with these simulation environments, you can do thousands of tests without involving people. Different ways to produce tests, and they could be based on models like the underlying models I showed you for the formal verification on the previous slide. They could be done in a pseudo-random way, and often there are tools to look at you know, how much of the system has been covered by these. I can see there's a paper from one of our colleagues at Bristol Robotics Lab and the University of Bristol, Kirstin Edder. So the work I've been involved in this was led by Kirstin and her team. End user validation then. So this involves, you know, experiments and interactions with users using practical scenarios. So we want to involve interactions with robots and humans, you know, and usually there's some form of hypothesis. An experiment is designed and along with users, and it helps work out whether human participants, for example, think robots are safe, trustworthy, etc. Here's some images at the bottom from the robot house at the University of Hertfordshire. So this was related to the Trustworthy Robots project. This team was led by Kirstin Douterham, who has now moved to Waterloo University, but the robot house still is there at the University of Hertfordshire. And I believe, you know, you can try experiments out in there if you contact them. And this is an image from the Trustworthy Robots project from Bristol Robotics Lab with their robot Bert. Okay, so this is my attempt to think about ideas, how are we going to do verification for autonomous robots, and some of the things that the group have come up with over the past few years. So there's 5 things on there. So I've got design for verification, look to other domains, corroborative verification, heterogeneous verification, and dealing with a small amount of learning. So on to the first of those, that's design for verification. So when we first started these robotics in hazardous environments, hubs we've been calling them, so you might hear me talk about hubs. One of the first meetings I went to, one of the collaborators said, oh, when I've finished my robot that does, you know, something, shall I just send it to you to verify? And, you know, I think the key thing we want to work with people that actually work with, that design and implement robots, is we probably need to think about design before the robot is constructed. We can look at verification after that, as some of these projects have done, but design for verification. And the first thing on my wish list is requirements. So it's good to, well, we need to know what the robot should do. And this goes back to the diagram I showed before. So we've got the stakeholder needs. What's the, what's wanted in the first place? We want to have some formal specification of what the robot should be doing. So what should it be doing or shouldn't it be doing? And what properties, things like in terms of functionality, things related to, around that robustness, reliability, standards, usability, safety, security, etc. So we need to know what the system should do before we can try and verify it. And again, some collaborators have said to us, we just want you to verify it. So we need to know what it should do to be able to verify it. Here's a couple of places where the team have had a look at requirements. It's one place, I think. So again, it's back to this grasping algorithm that Marie did with Nikos and Yang, who both were from the University of Surrey. Nikos has moved to York now. So this is trying to do active debris removal. So here's the real system, here's the simulation of the system. And the idea is there's a robot arm and it tries to grasp a particular object as it's going by. When Marie first was discussing this with Nikos and Surrey, I don't think there were many requirements around at all. So what Marie did with Nikos then was propose some, have a look at the system and then propose some requirements that they could try and then prove for this particular algorithm that was developed at Surrey. So two of the main requirements were get the best grasping point and draw the actual object closer, and that while doing that, you shouldn't collide with the thing that you're trying to actually grasp. So what Marie and Nikos did, they used a tool called FRET, and here's an example of the interface here. And this came from NASA, and this helps you go from natural language to formal logic for your requirements. And I know you can't read this, but there's a whole load of requirements that Marie and Nikos developed for this grasping algorithm that then they went on to try and verify. Okay, next in my wish list for design for verification is modularity. So I think, this is probably something that a lot of robot engineers and software engineers do anyway. So that's a good thing. So it's good to have architectures that are modular and we can separate out key components. So we need that to be able to do verification, but also for things like design, analysis, compositionality, maintenance. So here's a particular architecture. We've got an agent here. We've got a planning system. We've got some sensors going on. We've got some wheels. We've got a motor. Maybe the wheel breaks and we want to put another wheel in place for that. And as we'll see later when I talk about heterogeneous verification, different types of verification might be more appropriate to different components. So maybe we want to do testing on this. But for the planner and the agent, we probably want to do something more formal verification as well as testing. So that was modularity. Still for design for verification, we'd like to separate out the decision-making aspect. So I've called this a rational agent, but the thing making the decisions from the low-level control. So probably we want something like a rational agent. It's making the high-level choices. It's making decisions. It's looking at goals. It's selecting plans. It's doing prediction. And we want to separate that away from the low-level control. Things like sense and act, avoidance, being reaction. So this thing we probably want to do a lot of verification on. We want to make sure it follows, it really does the right thing, given the inputs it's got from the low-level control. So we probably want to formally verify this, but we probably don't want, or it's difficult to formally verify this part. And I've got some examples from FairSpace coming up. So this is the space environment. So here again is the Mars Curiosity rover. As I said before, this is the simulation is from NASA, and Raphael got hold of this, and along with, I think, Louise Dennis, put an agent to control this. So originally it was teleoperated. So Raphael and the rest of the people working on this used an agent in here, used the Gwendolyn system as an agent there, and they did some formal verification of the properties using Agent Java Pathfinder, and that was developed by Louise Dennis, that particular model checking system. So what they had the rover doing was moving around a whole bunch of waypoints, and what this is saying is it's always the case that if the rover agent moves to waypoint X, then at some point it decides to move to waypoint X, and at some point in the future the rover believes they will be patrolling the point X, and this was proved with this system here. So this involved putting an agent controlling this simulation rather than it being teleoperated. A second example, and when I was looking through the list of papers, I can see some people interested, I think it's later today, on human robot teamwork. So this is in the lines of that. So it was modelling human astronaut teamwork here. And this was done by Matt Webster, who's now at Liverpool John Moores University. So what Matt did is use some missions that he found from NASA to generate again some requirements and some properties that we've got in this particular table here. And Matt modelled the scenario. It was there was a habitat, there was an astronaut. The astronaut had to go out with the rover and do some mining and some inspection, take samples, that kind of thing. They had to go back to the habitat. When they were in the habitat, the rover had to make sure that the surroundings of the habitat were secure. So various things along those lines. Matt modelled this using Brahms. So Brahms is an agent modelling language. It was developed at NASA first, and one of the students, so Richard Stoker at Liverpool, designed a translator that translated from this Brahms language into the model checker spin, the input for the model checker spin. And Matt then managed to prove various properties that the rover and the astronaut were doing the right thing. So that was a little bit about decision making with some space examples. The next thing that was in my wish list, so moving away from design, was looking at domains. So having worked very closely on the RAIN project with people doing, oh, that's not a nuclear one, doing work robots in nuclear, on the Fair Space project, looking at things in space. And this is supposed to be representing the Orca project, so oil and off-sea energy and things like that. We noticed as a team that, you know, we were working across these projects, that there was a lot of kind of siloing going on. We can only look at robots in nuclear, or we can only look to robots in space, or we can only look at robots in the offshore environment. And as far as verification and validation were concerned, a lot of the things we were doing fit across these different domains. So all the things I've talked about, modularity, having requirements, a separation out from decision makings. It doesn't matter what domains we're in, but you know, those are useful for all those domains. So I'd say, you know, look to other domains. Are there any good things going on with respect to verification and validation in other domains? You know, can we look at logistics and transport? Can we look at agriculture? Can we look at domestic robots to help all of these things? So I think the slogan we were using in the group is you're not special. They may be special to some extent, but can we, you know, lift above the particular domains and share the problems and share the solutions? Okay, the next thing, corroborative verification. So this came out of the Trustworthy Robots project. And as I say, this was done when the team was at the University of Liverpool. So University of Liverpool, now Manchester, Bristol Robotics Lab, and the University of Hertfordshire. So what we looked at, we developed and applied 3 approaches to verification and validation of robot assistants, and we were aiming to increase trust in those assistants. and mostly Liverpool concentrated on formal verification. Simulation-based testing was mostly done by Bristol Robotics Lab, so Kirstin Edder, Tony Pipe and their team, and end user validation done by Kirstin Douterham and her team at the University of Hertfordshire. Bristol did a little bit of everything, if you want the truth here. And we had two use cases. So the first use case was the robot house at the University of Hertfordshire, and we used this thing, which is the Care robot. And the second use case was collaborative manufacturing, and this was done at Bristol Robotics Lab, and we were interested in a particular handover task that I'll talk about more in a couple of slides. So the first thing we had a look at was robot assistance in the robot house. So here's a couple of images of the robot house, and here's a plan of the robot house. I know it's very small, but essentially how this looked: there was a dining area, there was a kitchen, there was a hallway, there was a bedroom. In the dining in the house in general, there were many sensors doing things like saying whether people were sitting on the sofa, whether the television was on, whether they were sitting on the chairs here, whether the doorbell was ringing, whether the cupboards were open in the kitchen, whether the fridge door was open, my favorite one, etc. So there were sensors around that gave us gave the robot the state of the house and the occupants within it. It's essentially a domestic house. It was located in just a standard housing estate with human neighbours, and then in the house was this thing, the Care robot. So the Care robot is a commercially produced robot. It's by a company called Fraunhofer, so you can go off and buy one if you want. So essentially how this worked was that low-level actions, things like moving the wheels, etc., were controlled by high-level groups of rules. And these rules were put together to define behaviours. So here's one of the behaviours I'll talk you through in a minute. What this robot could do: it had a tray, it could move up and down, it had lights that flashed different colours to denote things, its torso moved, it had a graphical user interface where the user could choose between options. You can see this arm, we never used this in our experiments. I think the ethics agreement for this was quite hard to get, so we never used this particular arm here. It's quite big, so it was, I don't know, maybe a bit smaller than me, but it's quite a substantial robot. Here is one of the behaviours that controls the robot, and so this was developed at the University of Hertfordshire. So there are a whole bunch of these we looked at. There were two sets of them. We focused particularly on one that had 31 different rules, and this one was about the fridge door being open. So it goes something like this: if the fridge door's open, and so they're precondition action rules. So there's a whole bunch of things that have to be true, and then there's a whole bunch of actions. So if the fridge door's open and it's been open for more than 30 seconds and a particular flag is false, then what do? The robot light should turn to yellow. The robot should go to the living room. The robot should say the fridge door's open. Various flags are set to false. A graphical user interface shows the choice between go to the kitchen and wait here, that the user then chooses, and after a choice has been made, the another flag is set to true. So the decision-making aspect of this, there's a whole bunch of these. There were 31 we looked at. I think the other set had slightly more of these. Each of these have priorities. So this one, and the priorities I think were between 0 and 90. And the priority of this particular one, I think, was 60, if I remember. They also could be interruptible or not. So if they were, so essentially how the algorithm goes to choose which of these behaviors, that they operate one at a time, to which of these behaviors operate. So at any particular point, the system checks which of these left-hand sides or which of the conditions are satisfied, and then it will execute the one with the highest priority. If the highest priority, there's more than one with the same priority, then it just picks one between them. If they're interruptible, if this one wasn't interruptible, but if it was interruptible, if a behavior with a higher priority, the preconditions become true, the first one's suspended, and the new behavior then is operated. So that's an idea of how these things work. And these were stored in an SQL database. So what we did when we first saw this, so I did this, this was done by me and a colleague, Matt Webster, who I've mentioned already. And we worked closely with Kirsten Douterham and her team, particularly Joe Saunders, who went through the details of these behaviours a lot with us. And what we did was we decided we'd have a go using model checking. We created a model that represented these behaviours, and we tried to prove some things. So as we said before, it would have been nice to have some requirements for this particular system, but what we used for our properties here were things that should hold depending on how we believe this decision-making algorithm worked. So for example, we had things, the fridge door was open, this had been on for 30 seconds, this particular flag was false, and this behavior was scheduled. Then, for example, at some point in the future, you'd go in the living room. So we could prove various properties here. A couple of things on our experiences doing that. We didn't, you can see there's some properties related to timing here. So we didn't do very much in relation to timing. We abstracted away a lot of details related to timing. So we didn't do such a good job on that. And various things were abstracted away from. The second version of this, one of my students, Paul Gaynor, made a tool that read in direct from the database and output a model in the model checker new SMV directly, and it had various parameters, so you could parameterize this depending on the times that we had here. So that has two advantages. There wouldn't be any advantages of Matt and I getting it wrong because we handcrafted this by hand, and it gives you more, not scalability, but parameterization depending on these timings. Obviously, if you have timings in very small time units, 1 second, 2 seconds, we encounter this state explosion problem and the model gets too big. Anyway, we could prove things that we should be able to, and we didn't prove things we shouldn't be able to. The question here obviously is, what bugs did you find? So we did find a bug on the setting of one of these flags in these behaviours, but we did find it because Matt and I spent a lot of time looking at these rules and discussing them with Joe. The second thing then we did in relation to this was experiments in the robot house. So we actually did this particular experiment I'm going to tell you about using this robot. I think the Care robot was being fixed at the time. So this is the sunflower robot. And this was an experiment done with Kirsten Douterham and her team, and Kirsten and the team experimented with 40 participants using 2 scenarios in the robot house. So the scenario went like this. So you were invited round to lunch in the robot house, and the robot greeted you at the door. The person that had invited you had popped out. The robot greeted you at the door and guided you to the sofa, which you can see in the corner here. The robot then asked whether you wanted some music playing, and which type of music, rock or classical. Then it asked you to go and help set the table for lunch. It asked you to throw away some physical post that was written on, that was lying about on the table. There was some orange juice on the table that it asked you to pour into a plant. It then invited you to log on to the user's account to look for recipes, and then passed on their password and suggested that perhaps you might want to read their email. The thing about that, we had two scenarios. The thing about whether the robot was faulty or not was established in the first few minutes. So if the robot was supposed to be faulty, when it was guiding you to the sofa, it got lost in a corner and turned around several times. And if you asked it to play rock music, either it wouldn't play you music or it would play you classical music. So it didn't follow you instructions. The non-faulty version did all these things correctly. So as we say, Kirsten and her team did an experiment with 40 participants. And in both scenarios, the person was asked to carry out the setting the table tasks and the other things that I've mentioned. So the outcome from this was that although the errors in the robot's behaviour were likely to affect the participants' perception of its reliability and trustworthiness, it didn't seem to influence them whether they complied with the instructions or not. So clearly, we shouldn't really be logging onto other people's systems with their password. Probably we wouldn't want to be throwing post away or putting orange juice on plants either. And they're willing to comply with these instructions seem to depend on the task, in particular, whether you could reverse it or not. So given those first two forays into formal verification and, end user requirements, user validation, we came up with this, and this was work in particular done with Bristol Robotics Lab and Kirsten, Edda, Tony Pipe and their team. So this is corroborative verification. So we've got the three things we talked about: formal verification, simulation-based testing, and end user experiments. We've got underlying system models, so state transition systems or automata for formal verification, the simulator for simulation-based testing, and the physical system for experiments. And here are properties that have come from our requirements. So for formal verification, these are logical properties. For simulation-based testing, we've got assertions. And for end user experiments, we've got things written in English. And the idea with these things, looking at the axis, this is an abstraction, as I said before, and we get closer to the real world here. Yeah, these are more detailed as we go in this direction, but less precise. So we've got semantics for the things here. And the idea for these three things is to use outputs from experiments to help the other two. Outputs from simulation-based testing to inform experiments and formal verification, and similarly with formal verification. So here goes. This is what we did. Keeping an eye on the time. I'm clearly seeing I'm going to run out, but anyway. So the focus here was on this handover task you've seen before. So this was Bert, the idea that the robot had the robot arm, the chair leg here, and the robot was trying to pass over this is David Weston in the picture here. And what the robot's trying to ensure before the robot lets go of the table leg is that the person is looking in the right direction, and this is done from sensors on the hat here, that the person's arm is in the right place, the person's hand is in the right place, and there's sufficient grip on that table leg. First, we did some modelling using probabilistic timed automata. So I think there were, 9 or 10 models that looked like this. And some verification was done using the PRISM probabilistic model checker. So I think Matt was involved with Matt Webster with the PRISM model here. Simulation-based testing, this was Kirsten and her team. So she developed a simulator using the ROS framework for the robots and using Gazebo. Different ways of pushing those tests were done using models, and I think they used these probabilistic timed automata to do that, and pseudo-random, and yes, I've said that before. And what came out of this doing the simulation was that it revealed that the robot sometimes dropped the table leg accidentally. So that was new information, gripper failure. In the real robot experiments, then there was a small user validation, 10 participants carrying 10 handover tasks. They were given clear instructions and they were encouraged to complete the task successfully. So what this revealed was there were false negative results for the pressure and location sensors. So the pressure of the hand and the location of the hand. So why they were wrong, they wrongly reported as being too low or incorrect when they were in fact correct. So what can we do with this with respect to corroborative verification? Well, we had a look at the requirements, and these were inspired by ISO requirements, and we were interested in whether 95% or 60%, depending on different scenarios, of the handover attempts were successfully completed. So as I said, there was some disagreements between the outcomes that needed further investigation. So one thing was this thing from simulation-based testing that the robot dropped the table leg accidentally sometimes. This wasn't modeled in formal verification, so we changed the model for the informal verification. And the real robot experiments revealed false negatives for the pressure and location sensors that needed to be modeled in both the other systems. So the other point from this is some techniques were not suitable for verifying some of the requirements. So for example, speed or closeness, formal verification wasn't the best technique to use. Okay, so that was a little bit about corroborative verification. So trying to use different types of verification together to improve the models and improve the verification all round. Moving on, I've only got a couple of slides for heterogeneous verification because there are other experts in the room who are more expert than I am at this. So essentially, this is work done by Marie Farrell, Matt Lecoq, Raphael Cardoso, Louise Dennis, Michael Fisher. I'm sure if I've missed anyone, you can put that in the chat. The idea here is to use different or possibly more than one verification types for different components. So model checking or theorem proving for things like algorithms, programs design, testing for either software or simulation based, as we've seen. Experiments with robots, perhaps in a laboratory or in the intended setting, and combine these to get a confidence level for the whole system. So I think this work is still ongoing, so watch this space. So the idea, as we said before, split the system up into modular systems, specify what the subparts do, and we use appropriate verification testing techniques on each part. So for the vision system here, we're suggesting software testing. For the planner, maybe model checking. For the reasoning agent, perhaps theorem proving, and the hardware, simulation-based testing, for example. What Matt, Marie and the rest of the team then are proposing are using first order logic to specify assumptions and guarantees. So this is what's at the beginning and end of each of these boxes. Then apply relevant verification techniques to show that for all the inputs and for all inputs and outputs, given the assumptions eventually imply the guarantees. And then for the system altogether to see what we can show, we can prove about the system altogether, and to try and give us some confidence in the overall verification of the system, given the different verifications that have been done on each of these. I know I've been very vague and high up. I haven't really been involved in this, but I think this is a really good idea and it's something people should be aware of. So I'm sure Matt, Marie and the rest of the team can say more about that. I'm running out of time, but I'll try and quickly do a slide on learning and then sum up. So learning new behaviours, it's not learning. I know we've got something about machine learning tomorrow. So this is back to our robot example, learning new behaviours. So the robot had an interface to personalize behaviors. So all those primitives, things like the fridge door is open, someone seated on the sofa, the kettle is on, the television is on, they're all primitives in a system. And, you know, the actions, turn the lights to yellow, move to a particular place. You can put those together and add those into the robot system. The problem with doing this, so you can do that, you know, you can personalize the robot, putting these primitives together in different ways. The problem with doing that is some existing behaviors or the behavior you've just added will never run. And why is this the case? Let me just go back to my behavior. So here's my behavior, and I think I said it had a priority of 60. Well, imagine if you look at these left-hand sides here, and you input a new behavior, and it just had a precondition of the fridge door being open. Didn't have these are the preconditions. You decided it had a priority of 90. So whenever the fridge door, well, whenever all of these conditions were true, we know the fridge door must also, the fridge door is open must also be true. So the new behavior with just the one condition would always run in priority to this one. So this one would never run. So I'm just looking at the left-hand sides here and the priorities of behavior. And this is fairly confusing to users because maybe the thing that they've added would never run, or maybe some of the existing ones would never run. So what we did, we worked with Joe Saunders, there's a picture of him, and Matt Webster wrote this little algorithm. So we developed a static check on those left-hand sides. It related to the preconditions that you have to check and the priorities to make sure that behaviors were, you know, if you added a new behavior, that actually it was possible to run, or it didn't stop another behavior running. We reported this using a user experiment, and what the users said, it was significantly more useful in understanding and resolving the interference than and you didn't need much technical background than if we hadn't done that. Okay, I can see I'm kind of coming to the end of my time slot, so I think I should probably conclude. Apologies if that's been a bit rushed. So a summary of what we've talked about. We gave an overview to the research carried out on several projects on how to verify autonomous robot systems. So I believe design for verification is key. Rather than doing verification at the end, we need to think about how we're going to do that as we construct systems, state the requirements, have modular robot architectures, and have a separation of decision-making components from low-level things. We'd encourage to look beyond the domain you're working in for what's worked well and what hasn't worked well. We advocate using a suite of verification and validation techniques to help gain the assurance of the robot's safety, reliability, functional correctness, and all those other things. We discussed how this would work with corroborative verification. In particular, we looked at model checking along with simulation-based testing and user validation. And the idea we'd use each of those verification techniques to inform the others and improve them, and then redo the verification in kind of a cyclical approach. I talked very quickly about heterogeneous verification. So again, I think Matt and Marie could probably say a little bit more about that. And very briefly about personalization of robot behaviors, and a little bit we did to make sure that behaviors weren't stopped from running, or new behaviors wouldn't run at all. There's a few things I haven't had time to mention here. So runtime verification I mentioned at the beginning, and as I say, Raphael and Angelo I think are going to do a talk later on. So they've done, Raphael and Angelo certainly did apply some runtime verification to the grasping algorithm that I mentioned before, and also Mars Curiosity rover, probably lots of other things. We haven't talked about multiple robot systems or multiple sensor systems. So this was the other project, the Science of Sensor Systems software. And one of my colleagues, George Curtis, has been looking at using first order temporal logic to model either sensor systems or multiple robot systems. We haven't talked about combinations of verification with security. So we did this on the FairSpace project. So again, Marie Farrell was looking at this in collaboration with colleagues from the University of Warwick. Lots of work going on in the hubs with regulators. So Matt Lecoq will be able to tell you lots of things, in particular in relation to the nuclear regulators. And some of the team were interested in human-robot interaction, in particularly Emily Collins. If I have missed anyone out, I should have missed out. I'm so sorry. Final challenges, and then I'll be quiet. Learning. How do we verify and certify systems that learn? How do we verify machine learning systems? The answer to the second one we'll hear more about from our speaker tomorrow. Standards and certification. We need to work with the regulators to get these things through and on the market. And we need to make sure that the certification routes are better suited for autonomous systems. Quite a few of the group are working with people that are involved with standards or standards bodies. Trustworthiness. People both over-trust systems, and there's a lack of trust. So how do we get the right level of trust? Design I've mentioned already, design for verification, and we need to construct toolkits to facilitate this. How do we model these hazardous, uncertain and unstructured environments? And with formal verification, we're always faced with the state space explosion. How do we deal with that? Thanks again to our funders and all the collaborators, UKRI, EPSRC, and the hubs were funded under the International Strategy Challenge Fund. Lots of, a few sample papers there and various image credits I've got in the last couple of slides. Thank you so much for your attention, and I'll pass back to the chairs for any question.
Thanks, Claire. It's a real life clap here. It hasn't been one of those for a while. That's great. So once again, thank you so much, Claire, for a really, really interesting talk and for a very appropriate first talk at FMAS 2021. So there are a few questions in the chat, so I'll ask them and then maybe you can answer them. So Margaret West has two questions. Her first question is, were there any formal safety requirements for the system or its components? And I think we were talking about the handover for the table leg.
Just going for the table leg, this one. So I think I don't think there were any formal requirements when we got this, but I think what Matt Webster and Kirsten and the rest of the team had a look at the ISO standards, and I think the main one I think there was a whole load of things we looked at, but the main one was this percentage of the handover attempts should be completed successfully. I can't remember if Kirsten's online. She might remember some of the other things in there. Kirsten Edder?
So Margaret has actually clarified. She said she was thinking of safety requirements, specification of IEC standards.
I suspect the work we did have, I mean, obviously we would normally have in there that we don't want the, the robot hand colliding, the robot colliding with the human, things like that. I can't remember in detail what we had because there were quite a few of them, but the corroborative verification paper was published. Where is it? It was published, it's down the bottom, I think. It's this one here. So it was published last year. I'd have to go back and check, I'm sorry. But yes, those things are important, really important.
Can I just intersperse here? What I should have said was there's a safety life cycle involved in the IEC standards. Now, they did a sort of generic standard in about 1905, and they've been applying it to various applications since then. I don't know. I should have checked if there's a robotics one. I think there's one for road systems, but not sure if there's a robotics one. I should have checked that. But there's a generic one which talks about a safety life cycle, and that coincides with what you said about having importance of design, because then the safety is integrated in all the various stages in the specification and in the design and so forth. That's it.
Thank you. That's really useful. And I think, as I say, Michael Fisher, Louise Dennis, myself, Marie Farrell are involved in various standards to do with, standards and standards bodies to do with trustworthiness, to do with robotics, and we're trying to get the message out there. So yeah, standards and certification really important.
I'll look it up and I might come back and type it in if I can find anything.
Brilliant, thank you.
Thanks, Margaret. Even if you could put it in the chat or even in the Slack, that would be really helpful for everyone. So the next question, Claire, is from Carlos Varela. He said, thanks for the great talk. Does learning imply that a system specification needs to change? And if so, do you need runtime verification? Like, as in, do you need runtime verification?
Well, learning, I think, is I cheated a bit with saying this was learning. So, is it learning? Well, you can put new behaviors in, but, it's very controlled learning. But I'm not an expert on learning. It worries me. I don't know what the answer is. So if you had a system that had a specification, it was verified, and then it's out in the wild and it learns things, I don't know what it should do. Or do you have the system that's learning in the laboratory up to a certain point and then it isn't allowed to learn anymore? I'm not an expert on learning. I find the whole thing a bit worrying, and maybe other people might be more expert on that. Runtime verification, yes, I think runtime verification again is useful. I think the problem with putting a lot of runtime verification on is it might slow the system down real time. So if you've got monitors, going back to the issue about safety, and we don't want robots crashing into people or things, they're clear things you could put as monitors in runtime verification, whether it's learnt or not, and the robot then would stop before you did crash into somebody or something. But if you have a lot of these monitors, my understanding is it slows the robot down quite a lot. I don't know what the answer is to that. How do we deal with learning? Maybe we can have a talk on that at next year's FMAS.
Yeah, great. I think Divya will talk a little bit about learning tomorrow evening, which will be morning for her. And there is another paper later today, again, evening for us, but morning for her. On a similar topic. So I'm sure I'm interested in that, to tune in again. So I don't think there are any other questions in the Slack channel. Everyone in the room is shaking their head at me, so that's a good sign. And but I of course have my own, Claire, and I promise I won't be mean and ask you about the things that I know about. So I was just curious, maybe you could talk a little bit about the kind of block in getting formal methods used more generally. So a lot of the projects that you talked about, there were collaborations with software engineers, developers, but not necessarily familiar with formal methods. So I wonder, could you maybe just talk a little bit about how that collaboration works?
Oh dear. So I think a lot of that, I think Marie's probably talking about, in the two hubs that we were particularly involved in. So, well, Marie and I mean by we, RAIN and FairSpace. And so, yes, there were robots engineers, there were domain specialists around. And I think there has been a tendency in robotics to get something up and running, do a few tests, and perhaps think, well, okay, we've got that sorted. So I think trying to get this designed for verification, to think about these systems before we build them. But the problem with these projects where we came along and there were existing systems already, so we had to go back And as you saw with the grasping algorithm, Marie and Nikos, where is it? Then went back and sort of tried to work out what the requirements for that should be. And I think a lot of the if people actually want these things to get to market and to be used in practice, I think people are kind of coming on board a little bit, trying to think, well, how will we certify them? And just doing a number of run-throughs isn't enough. I think there are some barriers because it does take time and you need expertise. Well, like anything, developing the robots, obviously you need a lot of expertise as well. But one answer I think is working together with different groups, so formal verification, robot engineers, domain experts. The other thing I know, Michael Fisher had his EPSRC network, which put a lot of people together. So people working on standards, regulators, verification people, designers, government bodies, putting them all in the room together, so we know that the other people are there and who are the people we are talking to. I think it's coming, but yeah, I think there are barriers, but multidisciplinary, I think, is the way forward, and talking to each other. Not sure whether it's the answer you wanted, Marie.
No, that's great. Thanks so much. So I think we're just out of time, unfortunately. If anyone has further, please put them in the chat or in the Slack, and we can get them to her, and hopefully she can provide answers if she has time to. Although, hang on, Claudio has a question. The late breaking question added in. So Claire, you mentioned in your talk that most of the problems are shared by multiple domains, and often techniques are reusable across multiple domains. On the other hand, while sharing the same needs, different domains may have particular challenges that require techniques to be significantly changed to address these challenges. What is your view on this?
So my view is let me go back to that slide. A lot of the things we found here, things like the separation in terms of verification and validation, separating of decision-making parts, using modularity, writing down the requirements, using different techniques. They weren't special to any of these domains. I agree that some of the domains might have particular things like, the space domain, well, communications may not exist or there may be delays. The nuclear domain should be, you've got to worry about the physical aspects of radiation on those robots. But a lot of the verification and validation techniques actually cross over. The environments might be slightly different. So I think a lot of the techniques will cross over, but there will be specific things to those domains. I'm not saying everything just translates from, this robot walking down the street to a nuclear environment, but a lot of the techniques, tools, and ideas will. So it's perhaps a level of abstraction.
Great. Thanks, Claire. And thank you again for a really great talk. We can clap again.